right, picking up where we left off last time, acid-base reactions. We've already done stuff with acid-base reactions. If you were super confused about how to do the calculations, you're always welcome to revisit and resubmit, especially if I haven't graded it yet, which is the case for all of us so far. So an acid-base reaction, also called an acid-base neutralization reaction or just a neutralization reaction, is when an acid reacts with a base, the two neutralize each other, and it produces water, and often a salt. Remember that a salt is just an ionic compound. There's usually one of those left over. There's not always one of those left over, but commonly there is some ions left behind. We can also get versions of this that are gas evolution reactions. Gas evolution reactions, the evolve here just means produce. So a gas evolution reaction produces a gas. This is typically seen as bubbling. Like a baking soda and acetic acid, vinegar. I'm just going to write vinegar. Volcano. It's like the little paper mache volcanoes. You add food coloring, baking soda, acetic acid, and it bubbles over and it looks like the volcano is erupting. That would be an example of a type of gas evolution reaction. Before we get into acid-base reactions, we need to define what's an acid, what's a base. One of our definitions of an acid and a base are from Svante Arrhenius, who I believe was Swedish. So Svante Arrhenius defined an acid as a substance that produces H+ in aqueous solution. Both of these parts are important. And maybe for Arrhenius, what we could think of is aqueous. It has to be in water for it to be an Arrhenius acid, which is also true for bases. So for Arrhenius, we're producing H+. We would recognize the H+ as the front part of any of our acids for this class. We can recognize an acid because it's got H in front. That H is why it's an Arrhenius acid for most of the ones that we've looked at. That H from the acid molecule is actually donated to a water molecule. So this H+ latches onto an H2O, and it forms H3O+. H3O+ is more stable in solution, and this is our hydronium ion. Most chemists use H+ and H3O+ interchangeably. We frequently use H+ instead of H3O+ because there's fewer things to write. It's just faster. But anytime that we see H+ in solution, we should know in our minds that it's actually H3O+, hydronium. We can also have polyprotic acid, the poly in front meaning many, the protic meaning protons, so many proton acids. Many proton acids. These have more than one ionizable hydrogen or proton. So for example, sulfuric acid has two H's in front because the sulfate has a 2-, so it needs two pluses in the front, so H2. This is a diprotic acid. The di here referring to the two hydrogens in front. Typically the way that it works is the number of hydrogens in front is the number of ionizable protons or ionizable hydrogens. That's not always the case, but typically that's how it works. So for things like HCl, there's just one in front, so it's monoprotic, mono for one, protic for proton. For things like H2SO4, H3PO4, they're di or triprotic. So that's for our acids. For our bases, again, Arrhenius means aqueous, so our Arrhenius definition of a base, a substance that produces OH-. And it's also in aqueous solution because this is our Arrhenius definition. So for our acids, it's the H plus. For our bases, it's the OH minus. An example of this would be something like sodium hydroxide. Sodium hydroxide is a strong base. It's going to dissolve to form it's going to produce Na plus in solution. It's also going to produce OH minus. Because it produces OH minus directly, and it's in water because it's aqueous, that makes it an arrhenius base. So again, arrhenius is aqueous. We've got H plus for acid, OH minus for base. There are also bases like NH3 that do not contain hydroxide ions. Since that doesn't directly produce OH minus, that might not qualify as an arrhenius base. Some bases can also produce 2 moles of hydroxide per mole of base. So something like strontium hydroxide is going to produce 2 OHs. We might call it dibasic, but you probably won't see that show up. The way that acids and bases react, especially for our arrhenius acids, the H plus from the acid, again, H plus is linked to acid for arrhenius, combines with the OH minus from the base. OH minus is linked to it being an arrhenius base, and those make water. H plus OH minus makes H2O. Or we could also write it as HOH. There are limited instances where that will be useful. So looking at an acid-base reaction, HCl plus NaOH, the H from the hydrogen chloride reacts with the OH from the sodium hydroxide. That makes the water, which we could rewrite as HOH. And then the chloride and the sodium get put together. In this case, it's salt, but it's also a salt. It's an ionic compound, so that's just the leftovers. Our net ionic equation for an acid-base reaction is pretty much always going to be H plus OH minus goes to H2O. Our net ionic equation, because the Na and the Cl were both spectator ions. They started off aqueous, and they ended up aqueous, so they didn't actually participate, and so when we get the net ionic equation, we toss those out. They would still show up in our complete ionic equation, but we don't need them for the net ionic equation. And this is I feel like not especially helpful depiction of acid-base reactions. All we're showing here is we've got our hydroniums, our H pluses, and our Cls. We mix them up with our sodium and our hydroxides. And then after that's all said and done, our sodiums and our chlorides are all that's left because we made the H2O clear. So they're like in the background, because there's water in there already. Here's some common acids and bases. Notice that all of our acids have an H in front. Notice that most of our bases have an OH on them. So OH is going to be present in many but not all bases. Typically, these are going to be strong bases. So you'll see the O, the OH, and you'll think to yourself, oh, that's a strong base. That's a bit that I reuse from class to class, why there was a giggle. Ammonia is also a base, but it's a weak base. Ammonia is NH3. And the little asterisk is referring to the fact that it can take a proton from water and produce hydroxide and ammonium. Let's write a molecular and net ionic equation for the reaction that occurs between aqueous HBr and aqueous lithium hydroxide. So to start, we are told that we have HBr. It's aqueous. We also have lithium hydroxide, LiOH, also aqueous. these are going to form what are we going to form? Any ideas? H2O as a liquid. The H2O is from our H and our OH. Those are going together to form H2O. And then what's left is lithium and bromide. LiBr, aqueous. Another way that you can solve these, this is a double replacement or double displacement reaction. It doesn't really look like it because the H2O looks like it's a new thing, but this is why I showed us that we could also write it in as H connected with OH. So if we wanted to, we could separate HBr and LiOH. Let's do that in blue. We'd have H plus Br minus lithium plus OH minus. And this is what we would do for our complete ionic equation as well. On the other side, if we were going to form the molecular equation, which is what we have as this top line, we would swap the hydroxide and the bromide. The H plus would go together with the OH minus. That's the same as H2O, so we're going to change that into H2O. And then lithium would go with the bromide. So you can follow the same procedure for a double displacement reaction, and that would look something like this. You have to remember that H plus and OH minus go together to form H2O. And then if we wanted to do the net ionic equation, what two chemicals are not doing anything? They're not changing from left to right. What's one of them? Bromide. What's the other one? Lithium. So the bromide, the lithium aren't doing anything. So our net ionic equation would be H plus OH minus goes to H2O. Something like that. All right, let's write the net ionic equation for the reaction between aqueous HCHO2, which is a weak acid, and aqueous NaOH. Okay, so we want the net ionic equation for a reaction between aqueous, this thing, which I believe is formic acid, HCHO2, which is aqueous plus NaOH, also aqueous, and this is going to go to produce some things. It would help us, especially since we haven't seen this thing before, it would help us to break this down into its ions. So this CHO2 is a polyatomic ion. It's a group. It's sort of like the small brother, the little brother to the acetate anion C2H3O2. So this is going to be H plus. We're going to get CHO2 minus. From the sodium hydroxide, we are going to get the sodium, so 1 plus, the hydroxide as a 1 minus. That might look something like this. To figure out how they recombine, we're going to swap the CHO2 minus, like it's a double displacement reaction, because it is. And that will turn into the H plus being with the OH minus. So H plus plus OH minus, that's H2O. And we've also got the Na plus with the CHO2 minus. And I don't know about you, but I love some cheese on tortilla chips. And this is even better. You like nacho, this is nacho too. In this case, this would be our salt, NaCHO2. Sodium formate, if I'm not crazy. That is, this top bit, this would be our molecular equation. This bottom part would be our ionic equation if we, or our complete ionic equation if we turn this H plus and OH minus to H2O. That's our complete ionic equation. Then we want to look at what's unnecessary, what's not participating. It's the sodium, it's the CHO2 minus. So we would get rid of those things. And what's left? H plus, OH minus, and H2O. So that would be our net ionic equation. We could have also gotten that if we remembered, I don't expect us to have remembered this yet, but if we remember that's our net ionic equation for an acid-base reaction. Sodium hydroxide is a base, formic acid is an acid. So we could have jumped directly to that without doing basically any of the other stuff. Questions about any of the parts for that? Okay, I'll just label these for later. I talked about them, but now they're written in 2. One of the places that we use these acid-base neutralization reactions is in titrations. So in a titration, the stuff we were doing last week or you're doing today, if you're coming for the makeup, is you take a substance in a solution of a known concentration. Oftentimes it's an acid, sometimes it's a base. That's reacted with another substance in a solution of, or sorry, that's usually a base and sometimes an acid. It's reacted with a substance in a solution of unknown concentration. So basically we've got like the solution that was in our burette, the tall, long, skinny thing. We've got the solution that was below where we weren't sure what the concentration was. And we can react those together until they're at their stoichiometric ratio, which we call their equivalence point. The equivalence point means that all H plus and OH minus have reacted. So any H plus that we had in solution has reacted with the OH minus that was in solution. The way that we saw this in our solutions was it turned pink because of the phenolphthalein indicator that we used. That's not always going to be the case. Sometimes you'll use a different colored reactor, something like that. The unknown concentration can be calculated using stoichiometry since we know that the H plus and the OH minus reacted together. We have equal H plus and OH minus. So that unlocks our ability to use stoichiometry to use the balanced ratio or the ratio from our balanced chemical equation. Because these are typically colorless, we add an indicator like phenolphthalein, which is spelled crazy style. There's just mysteriously another pH in there. So that's phenolphthalein. That's the indicator that we were using that turns fuchsia in the presence of a weak base, or in a weakly basic solution. And I'm going to box in this bottom point, number of moles of H plus equals number of moles of OH minus. Here's what's going on in an acid-base titration. Typically, we've got hydroxide in our burette. Some solution that we've made, we don't always know the concentration of our hydroxide. That's what the first part of our titration was. We were figuring out what the concentration of our hydroxide was. So we take our hydroxide, we add it into an acid. Eventually, these turn into water molecules. As we add them in, they turn into water molecules. At some point, we've used up now all of our H pluses. No more acids left in solution. And if we were using a weak acid in here, it's slightly basic, and that turns the phenolphthalein this fuchsia color. Ideally, we catch it a little bit softer pink than this saturated color. Here's an example calculation for an acid-base titration. There's a lot of pieces of information in an acid-base titration, so it's important that we be able to pull them out and pair them correctly. The titration of a 20 milliliter sample of an H2SO4 solution of, keywords, unknown concentration requires, so the 20 milliliters is H2SO4 and we don't know the concentration. This requires 22.87 milliliters of a 0.158 molar KOH solution. So I'll underline these. These go together to reach the equivalence point. You should typically see the equivalence point mentioned in these problems. That just lets us use the balanced chemical equation coefficients. So equivalence point means that the added H plus equals the added OH minus, or the H plus that's in the solution equals the added hydroxide. They reacted in their stoichiometric ratios. So the pieces of information that we were given, we had milliliters of a solution of KOH. And we also had 20 milliliters of our unknown solution. We are trying to find what is that unknown concentration in molarity. It's also important for this equation, and for many of these equations, that we use our brains to come up with a balanced chemical equation. We have KOH reacting with H2SO4. Those are our two reactants. KOH plus H2SO4. That's going to produce some water. It's going to produce some K2SO4. The products here actually doesn't really matter, but there's one piece of information that we would have to be thinking about to do that. We do need to know that we're making H2O. H2O requires a hydroxide, it requires an H plus. And our H2SO4 has two H's in front. Two protons in front needs to be balanced out with two hydroxides to make H2O. So we would have 2 in front of our KOH. 2 to make the OH minuses balance out with the H pluses. This would also result in us having a 2 on our H2O in the back. We can also just balance this like a normal double displacement reaction. So let's look at what that would look like instead of my janky shortcut. K plus OH minus plus H plus SO4 2 minus. We swap the hydroxide and the SO4 2 minus. We get our H plus OH minus plus K plus SO4 2 minus. So these might be the steps that we would go through if we were doing just figuring out what's the double displacement reaction. Put these back together, and we would have swapped and dropped to get the subscript of 2 for our K2SO4. So this is how we got to this point. I just did it in my head. Now that we're there, we need to balance it. So I'm going to rewrite that the molecular part. When we're balancing double displacement reactions, this applies here as well, we need to find two things that are not equal. So what's something that's not equal on the left versus the right? The amount of hydrogens is not balanced. That's true. What's another thing that's not hydrogen or oxygen that's not balanced? Potassium's not balanced. So I would start with potassium. We've got 1 on the left, 2 on the right. We add a 2 in front of our KOH to get to 2 potassiums. When we do that, we also change the amount of OHs that we have. And this is why, so we would balance OH next. Do we have any OHs on the right side? Ooh. It doesn't look like we have OHs on the right side. So this is why I was telling us that we can also write H2O as HOH. Because this shows us more clearly that we've got a hydrogen coming from our acid and we've got a hydroxide coming from our base. So we actually just have 1 OH on the right side, if we write it out this way. To get those to balance out, we need a 2 in front of our H2O, which is the same as HOH. That 2 means that we've now got 2 H's and 2 OHs. The 2 H's balances with the 2 H's from the H2SO4. We could also, another way we could maybe do this is balancing it as the complete ionic equation might also work. And then the last thing that we would check is the SO4, and we've got balanced SO4, 2 minuses, 1 of each. Do we have questions about how we did those steps? You don't have to do it this way. If you do it this way, I recommend you write H2O as HOH if it's an acid-base reaction. Alternatively, if you can identify the H's in front are ionizable, so like H2SO4, we've got 2 protons in front. That needs to be balanced out by the same number of hydroxides, so we would need a 2 in front of our KOH. That would be another way that you could get your stoichiometric ratio here. So the important piece of information that we got from this is that 2 KOH equals 1 H2SO4. That's how they're going to react. 2 potassium hydroxides will react with 1 sulfuric acid. This is important because we're trying to find the concentration of the sulfuric acid, and we've got everything we need to know about potassium hydroxide. We are going to start with potassium hydroxide. We're going to start with potassium hydroxide because we've got 2 numbers for potassium hydroxide. The number that I'm going to choose to start with is this 22.87 milliliters because it's 1 unit, and molarity is secretly 2 units in a trench coat. It's moles over liters. So starting with, I'm going to write it in green, 22.87 milliliters KOH. In order for us to use this ratio that we spent time coming up with, we need to have what units?
Mass. No, two.
Moles. We have to get it into moles, and so we need a way of getting milliliters into moles. And one of the things that we can do is we can convert that to liters. There are 1,000 milliliters in 1 liter. So this would be 0.02287 liters KOH. And this liters also shows up in molarity. So my favorite trick with molarity, 0.158 molar, rewrite it as moles over liters. This shows us that 0.158 moles is equal to 1 liter of solution. We've got liters. If we multiply by molarity, 0.158 moles over liters, the liters will cancel. Are we seeing the vision? Hopefully we're seeing the vision. And I'm going to shrink the balancing. Microscopic balancing. So multiplying by molarity. The other way that we can get this, we can rearrange our equation. We're trying to get moles. To get the liters to go to the other side, we multiply both sides by liters. It cancels out on the right side. Moles equals molarity times liters. It's the same thing that we got by doing the dimensional analysis approach, where we changed molarity into moles over liters. So it might look something like this. So multiplying by our molarity, our liters of KOH cancel. This now leaves us with moles of KOH. We have moles of KOH. We want moles of H2SO4. That's where we use our balanced chemical equation. We have the KOH goes on the bottom. We want the H2SO4. The H2SO4 goes on the top. I'll write them in with moles. So 1 mole of H2SO4 will react with, on the bottom, 2 moles KOH. The moles of KOH cancel. We now have moles of H2SO4. I will go ahead and get us a unit or a number out here. You can also tag on the last step here, but I think probably a lot of us would want to stop doing calculations at this point, or pause doing calculations. So 0.02287 times 0.158 divided by 2. And we have 0.001867 moles H2SO4. What are we finding? Molarity. Is moles the same as molarity?
No.
It's not the same as molarity. Moles and molarity are different. But moles is related to molarity. Molarity is moles over liters. So we can find molarity if we have moles and liters. Do we have moles?
Yes.
We have moles. Do we have liters?
Yes.
Sort of, right? We have 20 milliliters. We can convert milliliters into moles. So down here in the tiny little corner that I've got left, 0.0200 liters. We take our moles, we divide it by the liters. So the number that we got as our answer divided by 0.02, and our concentration 0.0903. molar H2SO4. Questions? Confusions? Did anyone get lost somewhere and they don't mind sharing? Yes.
Multiply the moles by the weight. Divide.
At the end?
Yeah.
Yeah, we take this moles and we divide it by liters.
Okay.
And that's how we get the molarity. There's one way that we can make this faster that some of you are not going to want to use because you'll get confused potentially. We do not have to actually convert to liters for either of these. So we don't have to do this divide by 1,000, and then over here I did a times 1,000. No, I did a divides by 1,000, but we're dividing. Anyway, it works out that if you're starting in milliliters and you're ending in milliliters, if they're both the same unit, whatever they are, you don't have to convert those units away because they'll cancel out. And if I remember, if we do another example, I'll show us that. But it works out so that they end up canceling. So that's acid-base titrations. It looks like a lot of steps. This bottom part is a decent amount of steps. It's similar to the grams to moles to moles to grams stuff that we were doing with stoichiometry before. What we've added on is we're doing a balanced chemical reaction part, and it's a little more confusing than our typical double displacement reaction. So it's sort of two separate problems going on at the same time. We also have some gas evolution reactions. So in gas evolution reactions, reactions that produce gas, two aqueous solutions mix, and they form a gaseous product that typically bubbles out of solution. Some reactions form a gas directly from the ion exchange. So for example, we take potassium sulfide and sulfuric acid. We get potassium sulfate and hydrogen sulfide gas, H2S. And this H2S is a gas. So how would we identify that gas evolution reaction? We would just have to know that H2S is a gas. H2O is a liquid, H2S is a gas. Others form a gas by decomposing one of the ion exchange products. So one of the things that we come up with, like H2CO3, carbonic acid. H2CO3 is how carbon dioxide is stored in like a can of soda, for example. Some of it is stored that way. And that turns into H2O and CO2 gas. That's the bubbles that are leaving when you're drinking a soda. So H2CO3 you would have to identify as, oh, that decomposes to H2O and CO2. So we take one of the oxygens, we take the other two oxygens, the carbon, the hydrogens. We're actually breaking up a polyatomic ion, which we don't normally do, but we're doing it here. There's other examples of this. So another example, sodium hydrogen carbonate can react with HCl to form water, a salt, and CO2. This is sodium bicarbonate, NaHCO3. So that's those baking soda volcanoes. Sodium bicarbonate is the same as baking soda. So those can also produce gases. And here's the full list of things that we would have to recognize for gas evolution reactions. So the sulfides produce H2S. So H2S, if you see that, it's a gas evolution reaction if it's in the products. Other things that have intermediates, H2CO3, H2SO3. These are very similar to each other. So if we're seeing H2CO3 or H2SO3 as one of our products, that's going to go on another step, and it's going to produce CO2 in the case of our carbonic acid, or it's going to form SO2, sulfur dioxide, if we're starting with our sulfurous acid, or if that's our intermediate. We also have things like ammonium hydroxide, that forms NH3. One of the H's comes off of the ammonium and combines with the hydroxide to form water. And ammonia would leave as a gas here, typically. These are kind of, you just have to memorize them. Personally, gas evolution reactions are probably one of my least favorite parts of Gen Chem. I'll probably ask us 1 or 2 gas evolution reactions. Probably will not show up as a free response question. It'll probably be a multiple choice question. Let's do an example. We want to write a molecular equation for the gas evolution reaction. Nice that we're told that it's a gas evolution reaction that occurs when you mix aqueous hydrobromic acid and aqueous potassium sulfite. Hydrobromic acid has hydro in front, that means it's binary. The brome part means bromine, so HBr. Aqueous. We also have potassium sulfite. Potassium is K+, sulfite is SO3 2-, so we need 2 potassiums. So K2SO3, and that's aqueous. To figure out what our products are, we need to swap our anions. So H+, Br-, K+, SO3 2-. We're going to swap the Br- and the SO3 2- to get the H with the SO3 2-. Swap and drop, we get H2SO3. And the other stuff is K+ with Br-, which we just combine 1 to 1, KBr. Do we have an intermediate? Do we have a chemical on our product side that can form a gas? Yes. Which one is it?
H2SO3.
Yeah, it's the one in red, H2SO3. So H2SO3 can form a gas. The way that it does that is it's going to form SO2. So the H2 is going to react, or is going to pair up with one of the oxygens, and then the SO2 is going to leave as a gas. We would have to just remember that this is one of our intermediates, the H2SO3 turns into SO2 plus H2O. Our carbonic acid did a similar thing, but it was CO2 plus H2O. And so we would have to rewrite this, because it's going to be slightly different. So I'm going to copy paste. I'm going to copy, I'm going to paste. Okay. So this H2SO3 would be H2O plus SO2 so bad at grabbing things. Grab, grab. And our H2O is a liquid. Our SO2 is a gas. Our KBr is a salt, and it is soluble, so it's aqueous.
So we shouldn't write the intermediate. We should just go straight to the final.
I would expect for a complete, or for a molecular equation, yeah, we would just go directly to the products. Now, is this balanced? It's not balanced. So it would probably be helpful for our sanity to balance it with the form up here, where the H2, where the H's are together, the SO3s together, before we've separated our intermediate into its two component parts. Otherwise, we've got bonus work to do for our brains. If we balance it using this top equation with our intermediate, it is the same as our double displacement reactions. So we're looking for something that is not balanced in this top equation. What's something that's not balanced? Bromine's balanced currently. It's got 1 and 1. Our hydrogens are not balanced. We've got 1 on the left, 2 on the right. So we need a 2 in front of our HBr. That's going to also change our BRs. Now our BRs aren't balanced. We've got 2 on the left, 1 on the right. We would balance BR next. So we need a 2 in front of our KBr. We would look at our potassiums, 2 and 2. Our SO3 is 1 and 1. We didn't put a coefficient in front of our H2SO3. If we did, though, we would have to put it in front of the H2O and the SO2. In this case, it's just in front of the HBr and the KBr. So we would just copy those in down here, and now that should be balanced. Alternatively, you could just try balancing this final form, this final version of our molecular equation. That might bring its own special forms of mental damage with it. Questions about any of those parts? So some stuff to memorize from this table could show up on the exam.